This QuickLearn Bullet defines duration, modified duration, and DV01 and familiarizes you with the principal applications for these measures. The formula for a bond's duration is shown here, where N is the bond's maturity in years, F is the payment frequency per annum, and PVCFT means the present value of the cash flow at the end of period T, which of course is nothing more than that cash flow size discounted in the normal way for T periods. And finally, PVTCF is the total present value of aggregate cash flows under the bond, which of course means the bond's price. One good way to think about duration is as the time it takes until the owner of a bond has received, in present value terms, half his original investment back, without differentiating between coupons and principal, on the basis that a cash flow is a cash flow. We now introduce modified duration, whose formula is quite easy and appears now. This means essentially that you take duration and discount it for one period at the applicable yield to obtain modified duration. Duration itself has useful applications in various areas of finance, such as portfolio management, but its real value for our present purposes is simply as a stepping stone towards the calculation of modified duration. We now turn to the use of duration, and more particularly modified duration, and the role it plays in estimating a bond's percentage price volatility as the yield changes. Modified duration gives us a first-order approximation of how much, in percentage terms, a bond's price will change given a small change, upward or downward, in its yield. If an 8% bond's modified duration is approximately 6.8, for example, it follows that a 1 basis point change in yields will cause an approximate percentage change in price of 0.068%, and a 10 basis point change in yields will cause an approximate percentage change in price of 0.68%. More generally, we can write percentage change in price equals minus modified duration times the change in yield. The minus sign reminding us of the inverse relationship between yield movements and price changes. Technically speaking, modified duration is closely related to the first derivative of the price equation with respect to yield. You should have noted the fact that in the formula we showed, reproduced here in the red rectangle, the left-hand side of the equation speaks very specifically of the percentage price change. This is a critical point. For bonds trading at par, the percentage change will of course equal the change in dollars, but otherwise we must be more careful. Assume a $100 bond has a modified duration of 7 and is trading at 80 rather than at par. Using the above formula, we would estimate for a 10 basis point drop in rates a gain in price for this bond equal to 0.8%, and this would be correct. But this means the bond price will increase by 0.8% of 80, i.e. by $0.64, rather than by $0.8. In other words, the bond's new price would be 80.64 rather than 80.80. A limitation of modified duration is that it uses a single annualized discounting rate for all cash flows occurring during the bond's life, without differentiating between different points of the curve. It follows that when we speak of a quote-unquote yield movement, we assume a parallel shift in the yield curve from its initial position, which of course rarely occurs in real life. To the extent the curve pivots towards the left by becoming steeper, or towards the right and becomes flatter, the use of modified duration as an estimate of the percentage price change becomes less accurate. We next show how tenor, coupon, and yield affect the bond's duration and modified duration. The key relationships are summarized in this table. As tenor increases, the duration measures increase, and as tenor decreases, the duration measures decrease. As coupon increases, duration measures decrease, and vice versa when coupon decreases. And as the general level of yields increases, the duration measures decrease, and vice versa when yields decrease. The following observations are also of interest. A zero coupon bond has a duration equal to its maturity, since all cash flows occur on the maturity date. Its modified duration would be slightly less than its maturity. Second, as we lengthen the maturity of a bond, its duration and modified duration increase, but at a decelerating pace. A bond with an extremely long maturity can be shown to have a modified duration that peaks at a value equal to the inverse of its yield to maturity. So to illustrate, a 6% bond trading at a yield of 8% and having a very long maturity, say 100 years, would see its modified duration peaking at 1 over 8%, i.e. 12.5. One last measure of price sensitivity closely related to modified duration is DV01, which stands for dollar value of 1 basis point. This differs from modified duration in two important respects. First, it assumes exactly a 1 basis point shift in yield, since it is for small yield movements that these types of approximations generally are most accurate. And second, it calculates the price sensitivity of a particular bond or a particular portfolio of bonds, taking into account the size of the position and hence producing a result in dollar terms rather than as a multiple. Thus, just as we can say for our 8% 10-year bond with semi-annual coupons that its modified duration when it is trading at par is approximately 6.8, we can also say, assuming the size of our position is $100 million, for example, that the position's DV01 is around $68,000. The advantage of DV01 is that first, it is perhaps easier to visualize a potential gain or loss amount expressed in currency units, and second, that the aggregate DV01 of two positions is simply the sum of each DV01 without need to worry about the relative size of each position and having to make some sort of weighted average calculation. Modified duration, on the other hand, would require such an adjustment. We have explained already that modified duration gives a first-order approximation for the bond's price change in percentage given a defined change in yield, and also that this approximation is highly accurate for modest changes in yield on bonds with short or medium-term maturities, but that it becomes less accurate as maturity extends and the yield movement is large. In those cases, it becomes necessary to introduce a second-order effect known as the convexity effect. Convexity is discussed in a separate QuickLearn Bullet, So we have reached the end of this bullet on duration.